Friends, in this new video we discuss about few properties of moduli, exponential form of complex number and argument of a complex number. Friend, yesterday in the previous lecture we have seen that the mod of z, if z equal to x plus I y, then mod of z is equal to under root of x square plus y square, and if z equal to x plus I y, z bar conjugate of z complex number equal to x minus I y. Now if z mod of z1 into z2 equal to, again we have mod of z square equal to z into z bar. This is known result to us. So let us compute mod of z1 into z2 whole square. So by definition this is equal to z1 into z2 mod into z1 into z2 whole square equal to, so this is equal to z1 into z2 into z1 into z2 bar, z1 into z2 bar, then z1 into z2 into z1 bar into z2 bar. This is equal to z1 into z1 bar into z2 into z2 bar. This is nothing but mod of z1 square into mod of z2 square. Now taking square root on both sides, here mod of z1 into z2 equal to mod of z1 into mod of z2. So we get this result, mod of z1 into z2 equal to mod of z1 into mod of z2. Similarly here we can prove that mod of z1 divided by z2 equal to mod of z1 divided by mod of z2. So here we have established this result, mod of z1 into z2 equal to mod of z1 into mod of z2. Now let us prove one problem regarding this modulus property. If z is a point, I am writing here, if z is point inside the circle, express centered at origin, with the radius, radius 2, with the radius 2, prove that mod of z cube plus 3 z square plus 2z plus 1 is less than 25. So here you can see that z is a point inside the circle centered at origin with radius 2, and we have to show that mod of z cube plus 3z square plus 2z plus 1 is less than 25. For this we apply the modulus property. So what is given? It is given that z is a point inside the circle of radius 2. That means mod of z is less than 2. Modulus is a mod denote the this is the radius of the point. So distance from z and origin. Z and origin is less than 2, and we have shown that here mod of z1 into z2 equal to mod of z1 into mod of z2. So this gives us z1 z square. If we write z square, mod of z square, then this is equal to mod of z into z, and this is equal to mod of z into mod of z, or this is equal to mod of z square. Similarly, mod of z cube equal to mod z cube. So we have this. By using the result established, we have mod of z1 into z2 equal to mod of z1 into mod of z2. So mod z square equal to, we get mod of z whole square, and mod z cube equal to mod of z cube. Again here mod of z cube plus 3z square plus 2z plus 1, this is less than equal to, by modulus property, mod z cube plus 3 into mod z square plus 2 into mod z plus 1. 1 is a positive number. So friend, here we have mod of z cube plus 3z square plus 2z plus 1 is less than equal to mod of z cube plus 3 into mod z square. So this is equal to, you can see mod z whole cube plus 3 into mod z square plus 2 into mod z plus 1. But mod of z is less than 2. So we put the greater value 2 for mod z. So this will be less than 2 cube plus 3 into 2 square plus 2 into 2 plus 1, and this will be 8 plus 3 into 4 plus 4 plus 1 equal to 8 plus 12 plus 5, and this is 25. So we get that mod of z cube plus 3z square plus 2z plus 1 is less than 25. So whenever z is a point inside a circle centered at origin with radius 2, we have that mod of z cube plus 3z square plus 2z plus 1 is less than 25. So this is about the modulus results. Now here we see that if z equal to x plus iy and x is equal to r cos theta plus and y equal to r sin theta, then z equal to r into cos theta plus I into r sin theta. This is equal to r common cos theta plus I into sin theta. By Euler formula, we know that e raised to I theta equal to cos theta plus I into sin theta. Now for this cos theta plus I sin theta, we replace e raised to I theta and we get z equal to r into e raised to I theta. And here if we take x square plus y square, then we get r square cos square theta plus r square sin square theta, r square common, cos square theta plus sin square theta equal to, this is equal to 1. So, we have r square and we get r equal to under root of x square plus y square. Now, if we take y divided by x, that is r sin theta divided by r cos theta, r get cancelled, sin theta divided by cos theta, that will be tan theta, and we get theta equal to tan inverse of y divided by x. So, friend, here this is the exponential form of complex number. In this exponential form, we have taken x equal to, in terms of polar coordinate, r cos theta, y equal to r sin theta, and we have this r equal to under root of x square plus y square, and this r is this theta equal to tan inverse of y divided by x, and this theta represent the angle that makes z with x axis in the positive direction, and r is a length of a radius of a vector z. This theta is called as a argument of a z. This is the important part. R is a radius of a vector z and theta is an argument of a vector. So, argument of a z means it is an angle. So, when we plot in the Argand diagram, suppose this is my z, then this distance is r, z having coordinate x comma y, and this angle is a theta. This angle theta with the x axis in the positive direction, in the anti-clockwise direction, we are calculating theta in the anti-clockwise direction, then this is called as a argument of z and it is denoted by arg z. And what is r? R is a radius of z. Okay. So, this argument of z, here we express it as in the two parts, argument of z equal to arg, capital ARG of z, arg of z plus 2n pi. This capital ARG of z is called as a principal value of this argument, principal value of argument, principal value of z. Argument of z means principal value of argument of a z. So, the difference in this principal value and argument of z is, it is given as argument of z equal to arg, principal value of argument of z plus 2n pi. So, what is the basic difference in this principal argument of z and principal value of argument of z? Argument of z we calculate in the anti-clockwise direction, but argument of z is the shortest distance or shortest angle measured from the x axis. It may be along in the clockwise direction or in the anti-clockwise direction. So, we take one example to calculate the principal value of argument of z. So, let us see, suppose find the argument of z. Let us take the problem, find the argument of z, find argument of z equal to -1 minus I. So, friend, here note that argument of z, if we directly calculate the argument of z, argument of z, that is theta equal to tan inverse of y divided by x. Here you can see that x equal to -1 and y equal to -1, both are -1. Note here this is equal to tan inverse of minus 1 divided by minus 1, and this is equal to tan inverse of 1, and tan inverse of 1 is 45 degree, that is pi by 4. But this is a wrong answer. We have to consider the point in which it lies. If it is lies in the first quadrant, then it is okay. When the directly we can take this is equal to tan inverse of y divided by x. But when it is in the second quadrant, this makes an angle, this is theta, but we are taking this from here. So here in the second quadrant, the argument of z will be pi minus theta. When we come in the third quadrant, the theta will be here, it makes with x axis, and in this case we are measuring from this x axis. So this distance will be pi, this angle will be pi, and this theta. So this will be pi plus theta, and here this is equal to, when the point lies in the fourth quadrant, this is total distance, this pi and this pi. So this is angle theta, and we have to take minus from this total, that is 2 pi minus theta. This is a argument. But when we measure here, you can see that we have taken all the distances from this x axis in the anti-clockwise direction. We have measured this here, this is theta, this angle makes with x axis is theta, and we have taken the total distance pi minus this distance theta. Okay. So we have measured along this anti-clockwise direction, but when we talk about the principal value, then we have to consider again the same part, that is we have to take into we can measure it from clockwise or anti-clockwise direction, and in this case when it is in the first quadrant, the process is same, the argument of z is same, that is tan inverse of y divided by x. When it is in the second quadrant, again we have the same value here, that is pi minus theta. And when we are in the third quadrant, but in the third quadrant it is changes. Here you can see that when we measure this angle, this will be longer instead of this direction. Okay. So when we measure the angle in the anti-clockwise direction, angle in anti-clockwise direction, we take positive sign. When we measure angle in clockwise direction, it is negative, we take negative sign. So this is the shortest measurement for this point, and therefore we consider minus pi plus this angle. So tan inverse of y divided by x, tan inverse of y divided by x, and here you can see that this is theta. So in the fourth quadrant we take it as a minus, since we are measuring from this direction. So tan inverse of y divided by x, and therefore when we directly calculate this argument, and this will be we have to take into consideration, we cannot take it as a directly minus tan inverse of y divided by x, but we should take it as a pi minus tan inverse of y divided by x, and pi minus y divided by x, this is equal to pi minus pi by 4. So this is equal to 4 pi minus pi divided by pi 4 is equal to 3 pi divided by 4. Okay. So we get this answer, but you can see that this point z equal to minus 1 minus I, lies in the third quadrant, it is not in the second quadrant, is lies in the third quadrant. So, we have to consider this as the argument as argument of z is equal to minus pi plus tan inverse of y divided by x, minus pi plus tan inverse of y divided by x minus pi plus tan inverse of y by x, that we have just calculated pi by 4. So, this is equal to minus 4 pi plus pi divided by 4, and this will be this is equal to minus 3 pi divided by 4. This is principal value of the argument, and argument of z is equal to principal value minus 3 pi divided by 4 plus 2 n pi. This is the argument of z. Okay. So, when we consider the argument of when we want to calculate the argument of z, we have to calculate principal argument, and we can measure the principal argument in both positive and negative direction. When we measure it from in the positive direction, take the sign as a positive, and when we measure the angle in the negative direction, take the sign as a negative. And also note the point in which the quadrant the point lies. That is, here we can see that this point is a minus 1 comma minus 1, which is lies in the third quadrant, and in the third quadrant the principal value of the argument is minus pi plus tan inverse of y divided by x. Actually, we consider this as a modulus of y divided by x. So, to avoid the ambiguity of the sign, and we have minus pi plus tan inverse of y divided by x in the third quadrant, and in the fourth quadrant it is a minus tan inverse of modulus of y divided by x. In the second quadrant it is same as a pi minus tan inverse of mod of y divided by x, and in the first quadrant it is as it is directly tan inverse of mod of y divided by x. We should not we do not have to care about the modulus in the first quadrant, since both values are positive, and therefore we can directly write it as a y divided by x. Okay. So, here you can see that the argument of this point z equal to minus 1 minus i is equal to minus 3 pi divided by 4 plus 2 n pi. So, let us represent this number in the exponential form. The number here z is equal to minus 1 minus I, and just we have seen that argument of z is equal to, what is argument of z, that is we call it as a theta is equal to minus 3 pi divided by 4 plus 2 n pi, this is value. Now, let us calculate r. Z is equal to r into e raised to I theta. This is exponential form of the complex number, and r is equal to what? R is equal to x square plus under root of x square plus y square. Here x is equal to minus 1, y is equal to minus 1. So, r is equal to under root of minus 1 whole 1 square and minus 1 square, that is 1 square, this is equal to 1 plus 1, that is root 2. So, this is equal to root 2 into e raised to I into here minus 3 pi divided by 4 plus 2 n pi. Here n is equal to, we have restrictions, n is equal to 0 comma plus or minus 1 plus or minus 2 dash dash dash. So, for this n is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3, like this. Z is equal to this number z equal to minus 1 comma minus I can be written in the exponential form as under root of 2 equal under root of 2 into e raised to I into minus 3 pi divided by 4 plus 2 n pi. Now, as we know that if we have two numbers z1 and z2, we can write they in the exponential form. If we take suppose my z1 is equal to r1 into e raised to I theta 1 and z2 equal to r2 into e raised to I theta 2. Suppose I have these two numbers, then let us take the multiplication of these two. Z1 into Z2 equal to, we have r1 into e raised to I theta 1, r2 into e raised to I theta 2. So, this will be r1 into r2 into e raised to I into theta 1 plus theta 2. So, this is the product, and z1 divided by z2 equal to r1 e raised to I theta 1 divided by r2 into e raised to I theta 2 equal to r1 divided by r2 into e raised to I theta 1 into e raised to minus I theta 2. So, this is r1 divided by r2 into e raised to I into theta 1 minus theta 2. So, z1 divided by z2 equal to, let us compute z1 raised to minus 1, z1 raised to minus 1, or if simply if z is equal to r into e raised to I theta, z inverse is equal to we write z inverse means 1 divided by z. So, we have r into e raised to I theta, this is equal to 1 divided by r into e raised to minus I theta. This is z inverse. So, whenever z1 into z2, we have z1 into z2 equal to r1 into r2 e raised to I theta 1 plus theta 2, z1 divided by z2 equal to r1 divided by r2 e raised to I into theta 1 minus theta 2, and for z is equal to r into e raised to I theta, we have z1 inverse is equal to 1 divided by r into e raised to minus I theta. So, these are the simple properties of exponential function. Now, let us see one, let us take one problem regarding this argument. Suppose verify the results or verify the identity, argument of z1 into z2 equal to argument of z1 plus argument of z2. So, we want to prove this. Friend, argument of, just we have seen that argument of z1 into z2 equal to, here if z1 equal to r1 e raised to I theta 1, z2 equal to r2 into e raised to I theta 2, then z1 into z2 equal to r1 into r2 into e raised to I into theta 1 plus theta 2. So, here argument is theta 1 into theta 2, but by definition argument equal to what? Principal argument plus 2n pi. So, we write it as theta 1 plus theta 2 plus 2n pi, where n is equal to 0 plus or minus 1 plus or minus 2, like this. Now, here z1, argument of z1 is equal to argument of z1 theta 1 plus 2n1 pi, suppose, where n1 is equal to 0 plus or minus 1 plus or minus 2. Then we can write it as argument of z1 into z2 equal to theta 1 plus 2n1 pi plus theta 2 plus 2n pi minus 2n1 pi, addition and subtraction. Okay. Now, you can see that this is nothing but argument of z. So, this is argument of z1 plus theta 2 into plus 2 into n minus n1 into pi. Now, if we take it as a, if we choose z2, argument of z2 is equal to theta 2 plus 2 into n minus n1 into pi, we have argument of z1 into z2 equal to argument of z1 plus argument of z2. So we have established the result, argument of z1 into z2 equal to argument of z1 plus argument of z2. Now let us prove one more result regarding this argument. Show that here we have to show that z raised to n is equal to r raised to n into e raised to I n theta, where n is equal to 0 plus or minus 1 plus or minus 2 dash dash dash. Now we prove this result by mathematical induction. For n is equal to 1, z equal to r into e raised to I theta. So this is if z equal to r into e raised to I theta. So it is a given to us by this is show z raised to n is equal to r raised to n e raised to I n theta whenever z equal to r into e raised to I theta. So whenever z is n is equal to 1, we have z equal to r into e raised to I theta. This is given. Now let us assume that this result it is true for n is equal to m. That means z raised to m is equal to r raised to m into e raised to I m theta. Now if we calculate z raised to m plus 1, we can write z raised to m into z. But what is z raised to m? R raised to m into I into m theta into what is z? R into e raised to I theta. So this will be r raised to m plus 1 into e raised to I into m plus 1 into theta. That is the result. The result is true for m plus 1. So whenever we have shown that it is true for n is equal to 1 by assuming it is true for n is equal to m, and we have proved that it is true for n is true for m plus 1, and therefore by mathematical induction it is true for all positive value of n, all positive values of n. Now what about the negative value? So let us prove it for 0 and negative values of n. You can see that if we put a z is equal to n is equal to 0, then n is equal to 0, we have z raised to 0, z raised to 0 is equal to 1, again r raised to 0 into e raised to 0, this is equal to 1. So 1 is equal to 1, the result is true for n is equal to 0. Now when n is negative, let m is equal to minus n, then z raised to n is equal to z raised to minus m, this is equal to we have z raised to minus 1 whole raised to m. M is here we have taken m is equal to m is equal to minus n, so m is positive, and for positive it is true. So we have 1 divided by z inverse, z inverse is equal to, just we have calculated 1 divided by r into minus I into theta. So r into e raised to minus I into theta whole raised to m. This is equal to r raised to minus 1 r e raised to minus I into theta whole raised to m. This is r raised to minus m into e raised to I into minus m into theta, we can write this. But r raised to minus m, what is r raised to minus m? This is n, and e raised to I n theta. So it is true for n negative values of n also. Hence for the exponential case, we have shown that whenever z is equal to r into e raised to I theta, we have z raised to n is equal to r raised to n into e raised to I n theta. Now friend, let us compute complex number power of the complex number, that is compute one problem, compute under root of 3 plus I whole raised to 7. Let us take z equal to under root of 3 plus I. Here x equal to under root of 3, y is equal to 1. Then we have r is equal to what? Under root of 3 square, 3 plus 1, this is equal to under root of 4, and this will be 2. And tan inverse of y divided by x equal to tan inverse of 1 divided by under root of 3, and this will be under root of 3, this will be 1 divided by so you can see that under root of 1 divided by 3, hence theta equal to here pi divided by 6, pi by 6. Then z equal to, by using z equal to r into e raised to I theta, we can write under root of 3 plus I equal to 2 into e raised to I into pi divided by 6. Now under root of 3 plus I whole raised to 7 equal to, you can write 2 raised to 7 into I into 7 pi divided by 6. Okay, so we write it as 2 into 2 raised to 6 into e raised to I into pi into e raised to I into pi divided by 6. Okay, so 7 pi by 6 I have written like this, pi plus pi by 6, pi plus pi by 6, and e raised to pi plus pi by 6, this is equal to e raised to pi into e raised to pi by 6. Okay, so like this. Now you can see that we write it as 2 into e raised to I into pi by 6, e raised to I into pi by 6 in one bracket, and 2 raised to 6 into e raised to I pi. Okay friends, now e raised to, what is e raised to I theta? E raised to I theta equal to cos theta plus I into sin theta. Therefore e raised to I pi equal to cos pi plus I into sin pi 0, cos pi minus 1. So we have minus 1, let us put this value, this is equal to, now why I have taken this 2 into I pi 6, look at this, 2 into e raised to I pi 6. So this is nothing but under root of 3 plus I into 2 raised to 6 into here minus 1. So we get this is equal to 2 raised to 6, 2 raised to 6 equal to 64, minus 64 into under root of 3 plus I. So this is under root of 3 plus I whole raised to 7. We get this under root of 3 plus I whole raised to 7 equal to minus 64 into under root of 3 plus I. So you can see that how exponential form is helpful to calculating the powers of the complex number. This example shows that by using this exponential form of complex number, we have easily calculate the powers of the complex number. So friend, here we stop. Thank you for watching and being with me.